So the last piece of the puzzle for the search with the parallel splitterator example will just be to evaluate the pros and cons of everything we've seen so far. I think you'll hopefully be in a good position to do this now that we've talked about a lot of different approaches. First, what's the good part? So the good part of this is parallel splitterators can help to transparently improve program performance even more. As you saw, the optimization was purely at the splitterator level. The intermediate operations didn't change. The terminal operation didn't change. The collector didn't change. Nothing else changed, just the splitterator. And one of the nice things about this is that this version ran faster than the parallel streams version on this particular platform, which had 4 cores and a 2.7 gigahertz processor. You can get even better performance if you have a faster processor. My Mac is a little faster, so it runs faster. Why is it faster? Why does it scale better? Because we have a finer level of granularity of parallelism. So we had more things that could run in parallel, and that was able to take better advantage of the underlying cores. So it's finer level granularity, smaller granularity of parallelism, which means more things that could be done at the same time. We're keeping the pipeline, we're keeping the threads in the common fork join pool busier, and so it's doing a better job of kind of achieving optimal speed up. Another nice thing, from the point of view of programming, just this code looked exactly the same. We just switched from true to false or false to true to make it run in parallel. Of course, and here's the dark side of this, it was not easy to implement that phrase match splitterator, especially the try-split method. So that did take some time. So with that caveat in mind, let's talk about the cons of this approach. So the downside is it was a lot more complicated to implement the parallel version of phrase match splitterator than the sequential version. The sequential version was trivial. We just used the pattern matcher, essentially. But the parallel version of the splitterator had a lot more moving parts. The split had to be done very, very carefully. If you look at that code, isn't at all obvious that it works. In fact, when I first wrote it, it didn't work. And so I wrote a bunch of unit tests to test to make sure it worked, and that helped give me greater confidence. But as you've all seen from the programming assignments, the tests are only going to get you so far, right? Sometimes the tests don't cover things thoroughly enough. Sometimes the tests have bugs, and so on and so forth. Which reminds me, I'm going to push out some fixes to the tests to fix a few of the weird glitches. And there's actually race conditions in the tests, if you can believe that. That's almost always the case when you have tests for parallel processes, parallel programs, because it's hard to test them. So ironically enough, writing the parallel splitterator actually took longer than pretty much writing the rest of the application. Everything else was really simple. Everything, as you see, if you look at it, it's all kind of canonical. It always looks the same. But the phrase match splitterator try-split method was the hardest thing to do and the most subtle. So that's not always the case. I think if you go back and you take a look at the array splitterator that you did for assignment number 2 and have improved a bit over time, that wasn't trivial. In fact, there's still people with a few bugs lurking in there probably. But it's not really all that hard. And once you get the gist of it, it's not too bad at all. Because it's basically just divide and conquer of an array, which is a contiguous data structure without a lot of special cases. Conversely, trying to split the input in such a way where the phrases don't get split across the chunks, that's a lot more subtle and tedious to write and test. Okay, so that's the end of the splitterator example.